In this lesson, we will evaluate the effect of cache block size on two different access patterns, 32 bytes versus 128 bytes blocks on two traces. Trace 1 is a sequential media decode, essentially a streaming read. Trace 2 is a graph breadth first search. We will use simple locality assumptions to estimate miss rates and bandwidth, both mathematically and graphically. For the sequential media decode, every byte will be consumed in order. A simple model says the miss rate for block size B is word size over B, MR equals E divided by B, with E equals 4 bytes. MR for 32 bytes is 4 over 32, which is 0.125. For 128 bytes, it is 4 over 128, which is 0.03125. For bandwidth per access. Each access ultimately transfers about 4 bytes from memory over time because the entire block is used, so traffic per access is MR times B equals 4 bytes per access in both cases. Let's see it graphically. On the left is 32-byte blocks. On the right is 128-byte blocks. We visualize 32 words. Each word is 4 bytes. As we sweep left to right, a miss happens when we enter a new block. Notice that for 32-byte blocks, we miss every 8 words, while for 128-byte blocks, we miss only every 32 words. Summarizing T1, the miss rate is lower for larger blocks, but bandwidth per access is the same, because all fetch data is used. Here are the bars for miss rate and traffic. Now consider trace 2, a graph breadth first search. We use a simple mix model. A fraction alpha of accesses are sequential scans over adjacency lists, and the remaining 1 minus alpha are random metadata checks like visited flags or queue updates. With this, miss rate of block size B becomes alpha times E over B plus 1 minus alpha times 1. Using alpha equals 0.5, we get for 32 bytes MR equals 0.5 times 4 over 32 plus 0.5 times 1 equals 0.5625. For 128 bytes, we get 0.5 times 4 over 128 plus 0.5 times 1 equals 0.515625. Bandwidth per access equals MR times B. That is about 18 bytes per access for 32-byte blocks, and about 66 bytes per access for 128-byte blocks. The larger block wastes much more bandwidth on the random part. Graphically, think of two kinds of touches. Random visited checks hit 1 byte scattered across memory. Fetching a 32-byte block means 31 bytes wasted right now. Fetching a 128-byte block means 127 bytes wasted. For the sequential neighbor scan, both block sizes give runs of hits after the first miss, but the 128-byte block runs 4 times longer. Since BFS is a mix, the waste on the random part dominates the bandwidth. Here are the bars for trace 2. The miss rate is only slightly lower for the bigger block, but the bandwidth per access is far higher due to wasted data on random touches. Let's put it all together. For sequential media decode, larger blocks like 128 bytes reduce miss rate and keep bandwidth efficient because we use everything we fetch. For graph breadth first search, the random part dominates, so 32-byte blocks drastically reduce wasted bandwidth, even if the miss rate improvement with larger blocks looks small. Recommendation under these simple assumptions: choose 128 bytes for streaming decode and 32 bytes for graph BFS.